A Short Account of the History of Mathematics by W. W. Rouse. Preface. The subject matter of this book is a historical summary of the development of mathematics, illustrated by the lives and discoveries of those to whom the progress of the science is mainly due. The first edition was substantially a transcript of some lectures which I delivered in the year 1888 with the object of giving a sketch of the subject that should be intelligible to anyone acquainted with the elements of mathematics. In this edition I have revised the whole and have made some changes in detail, but the general character of the work as a popular account of the leading facts in the history of mathematics remains unaltered. The scheme of arrangement will be gathered from the table of contents at the end of this preface. Shortly, it is as follows. The first chapter contains a brief statement of what is known concerning the mathematics of the Egyptians and the Phoenicians. This is introductory to the history of mathematics under Greek influence. But as the Ionian Greeks were considerably indebted to the Egyptians and Phoenicians, it is convenient to commence with a concise account of the attainment of the latter. The subsequent history is divided into three periods. First, that under Greek influence, chapters 2 to 7. Second, that of the Middle Ages and Renaissance, chapters 8 to 13. And lastly, that of modern times, chapters 14 to 19. In discussing the mathematics of these periods, I have confined myself to giving the leading events of the history, and frequently have passed in silence over men or works whose influence was comparatively unimportant. Doubtless an exaggerated view of the discoveries of those mathematicians mentioned may be caused by non-allusion to minor writers who preceded and prepared the way for them, but in all historical sketches this is to some extent inevitable, and I have done my best to guard against it by interpolating remarks on the progress of the science at different times. Perhaps also I should here state that generally I have omitted all reference to practical astronomers unless there was some mathematical interest in the theories they proposed. In quoting results I have commonly made use of modern notation. The reader must therefore recollect that, while the matter is the same as that for any writer to whom allusion is made, his proof is sometimes translated into a more convenient and familiar language. I am of opinion that it is undesirable to overload a popular account with a mass of detailed references. Usually, therefore, I have collected in a single footnote for each school or mathematician references to the chief authorities on which I have based my account or with which I am acquainted. And I have not given the authority for every particular fact mentioned unless I regard it as difficult to verify without a definite reference. I hope that these footnotes will supply the means of studying in detail the history of mathematics at any specified period, should the reader desire to do so. The greater part of my account is a compilation from existing histories and memoirs, as indeed must necessarily be the case where the works discussed are so numerous and cover so much ground. When authorities disagree, I have generally stated only that view which seems to be the most probable. But if the question be one of importance, I believe that I have always indicated that there is a difference of opinion about it. I have struck out the long list of standard histories which I published in the first edition. Most of the facts and opinions for the first and second periods into which I have divided the history are quoted or criticized in the closely printed pages of M. Cantor's elaborate Vorlesungen über die Geschichte der Mathematik, to which the reader desires further information on any particular point would naturally turn. To that work H. Henkel's brilliant but fragmentary Geschichte der Mathematik, Leipzig, 1874, and in a lesser degree F. Hofer's Histoire de Mathématique, Paris, 3rd edition, 1886, and to M. Marie's Histoire des sciences de mathématiques et physique, 12 volumes, Paris, 1883 to 1888. I am usually indebted, when no specific reference is given. I frequently refer to these works by the names of the authors only. For the last 2 or 3 centuries the general histories give but little assistance, and the student must rely mainly on special monographs. My thanks are due to various friends and correspondents who have called to my attention points in the first edition. No one who has not been engaged in such work can realize how difficult it is to settle many a small detail, or how persistently mistakes which have once got into print are reproduced in every subsequent account. I shall be grateful for notices of additions or corrections which may occur to any of my readers. W. Rouse, Trinity College, Cambridge, April 21st, 1893. This concludes the preface to the short account of the history of mathematics. Chapter 1. Egyptian and Phoenician Mathematics. The history of mathematics cannot with certainty be traced back to any school or period before that of the Ionian Greeks. But the subsequent history may be divided into three periods, the distinctions between which are tolerably well marked. The first period is that of the history of mathematics under Greek influence. This is discussed in chapters 2 to 7. The second is that of the mathematics of the Middle Ages and the Renaissance, and this is discussed in chapters 8 to 13. The third is that of the modern mathematics, and this is discussed in chapters 14 to 19. Although the history commences with that of the Ionian schools, there is no doubt that those Greeks who first paid attention to mathematics were largely indebted to the previous investigations of the Egyptians and the Phoenicians. This chapter is accordingly devoted to a statement of what is known concerning the mathematical attainments of those races, but our acquaintance with the subject is so imperfect that the following notes must be regarded merely as a brief summary of the conclusions which seem to me most probable. The actual history of mathematics begins with the next chapter. On the subject of prehistoric mathematics, we may observe in the first place that, though all early races which have left records behind them knew something of numeration and mechanics, and though the majority were also acquainted with the elements of land surveying, yet the rules which they possessed were in general founded only in the results of observation and experiment, and were neither deduced from nor did they form part of any science. The fact, then, that various nations in the vicinity of Greece had reached a high state of civilization does not justify us in assuming that they had studied mathematics. The only races with whom the Greeks of Asia Minor, amongst whom our history begins, were likely to have come into frequent contact were those inhabiting the eastern littoral of the Mediterranean, and Greek tradition uniformly assigned the special development of geometry to the Egyptians, and that of the science of numbers either to the Egyptians or to the Phoenicians. I will consider these subjects separately. First, as to the science of numbers. So far as the acquirements of the Phoenicians on the subject are concerned, it is impossible to speak with any certainty. The magnitude of the commercial transactions of Tyre and Sidon must have necessitated a considerable development of arithmetic, to which it is probable the name of science might properly be applied. According to Strabo, the Tyrians paid particular attention to the sciences of numbers, navigation, and astronomy. They had, we know, considerable commerce with their neighbours and kinsmen the Chaldeans, and Bach says they regularly supplied the weights and measures used in Babylon. Now the Chaldeans had certainly paid some attention to arithmetic and geometry, as is shewn by their astronomical calculations, and whatever was the extent of their attainments in arithmetic, it's almost certain that the Phoenicians were equally proficient, while it is likely that the knowledge of the latter, such as it was communicated to the Greeks. On the whole, I am inclined to think that the early Greeks were largely indebted to the Phoenicians for their knowledge of practical arithmetic or the art of calculation. It is perhaps worthy of note that Pythagoras was a Phoenician, and according to Herodotus, but this is more doubtful, Thales was also of that race. Next, as to the arithmetic of the Egyptians. Their civilization, and in particular their astronomical calculations, have been generally accepted as implying that they were fairly proficient in the science of numbers. But about 25 years ago, a hieratic papyrus forming part of the Rhind collection in the British Museum was deciphered, and this has thrown considerable light on the mathematical attainments of the Egyptians. The manuscript was written by a priest named Ahmes somewhere between the years 1700 BC and 1100 BC and is believed to be itself a copy with emendations of an older treatise of about 3400 BC. The work is called Directions for Knowing All Dark Things and consists of a collection of problems in arithmetic and geometry. The answers are given, but in general, not the process by which they are obtained. The first part deals with the reduction of fractions in the form of 2 divided by 2n plus 1 to a sum of fractions whose numerators are each unity. For example, Ahmes states 2 divided by 29 is a sum of 1 over 24, 1 over 58, 1 over 74, and 1 over 232. And 2 over 97 is a sum of 1 over 56, 1 over 679, and 1 over 776. In all examples, n is less than 50. Probably he had no rule for forming the component fractions, and the answers given represent the accumulated experiences of many previous writers. In one solitary case, however, he has indicated his method for, after having asserted that 2/3 is a sum of 1/2 plus 1/6, he adds that therefore 2/3 of 1/5 is equal to the sum of a half of a fifth and a sixth of a fifth, that is, 1 over 10 plus 1 over 30. The next part of the book is devoted to examples in division and subtraction. Ahmes then proceeds to the solution of some simple numerical equations. For example, he says heap its seventh its whole it makes 19, which means find a number such that the sum of it and 1/7 of it shall be together equal to 19. And he gives us the answer 16 plus 1/2 plus 1 over 8, which is correct. The latter part of the book contains various geometrical problems to which I allude later. He concludes the work with some arithmetico-algebraical questions, 2 of which deal with arithmetical progressions and seem to indicate that he knew how to sum such series. This appears to represent the most advanced arithmetic to which the Egyptians became acquainted. At any rate, it is all that they communicated to the Greeks. Throughout the work, Ahmes rarely explains the process by which he arrives at a result, but in one numerical example, where he requires to multiply a certain number, say a, by 13, he points out the method he has used. In this instance, he first multiplied 2 and got 2a, and then he doubled the result and got 4a, and then he again doubled the result and got 8a, and lastly he added together a, 4a, and 8a, a process strictly analogous to what is now called practice. The arithmetical part of the papyrus indicates that Ahmes had some idea of algebraic symbols. The unknown quantity is always represented by the symbol which means a heap. Addition is represented by a pair of legs walking forwards, and subtraction by a pair of legs walking backwards or by a flight of arrows, and equality by the sign, one that looks like a less than or equal to sign which is upside down. As we shall see in the next chapters, the Greeks shewed no aptitude for algebra, and it was not until the development of mathematics passed again into the hands of members of a Semitic race that any considerable progress was made in the subject. A large part of Ahmes's arithmetic is devoted to fractions. It may be noticed in passing that the treatment of fractions presented great difficulty to all early races. The Egyptians and Greeks reduced a fraction to the sum of several fractions, in each of which the numerator was unity, so that they had to consider only the various denominators. The sole exception to this rule being the fractions 2/3 and 3/4. This remained the Greek practice until the 6th century of our era. The Romans, on the other hand, generally kept the denominator constant and equal to 12, expressing the fraction approximately as so many twelfths. The Babylonians did the same in astronomy, except that they used 60 as the constant denominator, and from them, through the Greeks, the modern division of a degree into 60 equal parts is derived. Thus, in one way or the other, the difficulty of having to consider changes in both numerator and denominator was evaded. Before leaving the question of early arithmetic, I should mention that for practical purposes the almost universal use of the abacus or swan pan rendered it easy to add and subtract or even to multiply and divide without any knowledge of theoretical arithmetic. These instruments will be described later in chapter 7. It will be sufficient here to say that they afford a concrete way of representing a number in the decimal scale and enable the results of addition and subtraction to be obtained by a merely mechanical process. This, coupled with a means of representing the result in writing, was all that was required in primitive times. Second, as to the science of geometry. Geometry is supposed to have had its origin in land surveying, but while it is difficult to say when the study of numbers and calculation, some knowledge of which is essential in any civilized state, became a science, it is comparatively easy to distinguish between the abstract reasonings of geometry and the practical rules of land surveying. The principles of land surveying must have been understood from very early times, but the universal tradition of antiquity asserted that the origin of geometry must be sought in Egypt. That it was not indigenous to Greece and that it arose from the necessity of surveying is rendered the more probable by the derivation of the word from the earth and I measure. The Greek geometricians, as far as we can judge by their extant works, always dealt with the science as an abstract one. They sought for theorems which should be absolutely true, and would have argued that to measure quantities in terms of a unit which might have been incommensurable with some of the magnitudes considered would have made the results mere approximations to the truth. The name does not, therefore, refer to their practice. It is not, however, unlikely that it indicates the use which was made of geometry among the Egyptians from whom the Greeks learned it. This also agrees with the Greek traditions, which in themselves appear probable, for Herodotus states that the periodical inundations of the Nile, which swept away the landmarks in the valley of the river and by altering its bed increased or decreased the taxable value of the adjoining lands, rendered a tolerably accurate system of surveying ground indispensable, and thus led to a systematic study of the subject by the priests. The Egyptians certainly studied geometry. A small piece of evidence which tends to shew that the Phoenicians and Jews had not paid much attention to it is to be found in the mistake made in 1 Kings chapter 7 verse 23 and 2 Chronicles chapter 4 verse 2, where it is stated that the circumference of a circle is 3 times its diameter. The Babylonians also assumed that pi was equal to 3. Assuming then that a knowledge of geometry was first derived by the Greeks from Egypt, we must next discuss the range and nature of Egyptian geometry. For any accurate amount of this, we have to rely on the Rhind papyrus mentioned above. This, as I have already stated, was probably a summary of the information which was familiar to the priests, and was not a book of research. At any rate, we have reason to believe that some time before the year 2000 BC, that is, some centuries before it was written, the following method of obtaining a right angle was used in laying out the ground plan of certain buildings. The Egyptians were, we know, very particular about the exact orientation of their temples, and they had therefore to obtain with accuracy a north and a south line, and also an east and a west line. By observing the points on the horizon where a star rose and set, and taking a plane midway between them, they could obtain a north and a south line. To get an east and a west line, which had to be drawn at right angles to this, certain professional rope fasteners were employed, who stretched a rope round three pegs, the two of them which were nearest together being fixed along the north and south line, so that the sides of the triangle formed were in the ratio 3:4:5. The angle opposite the longest side would then be a right angle. A similar method is constantly used at the present time by practical engineers. This property can be deduced as a particular case of Euclid 148, and there is reason to think that the Egyptians were acquainted with the results of this proposition and of Euclid 147 for triangles whose sides are in the ratio mentioned above. They must also, there is little doubt, have known that the latter proposition was true for an isosceles right-handed triangle, and that it is obvious if a floor be paved with tiles of that shape. But though these are interesting facts in the history of the Egyptian arts, we must not press them too far as shewing that geometry was then studied as a science. Our real knowledge of the nature of Egyptian geometry depends almost entirely on the Rhind papyrus, and therefore at the earliest does not go further back than the year 1700 BC. Ahmes commences that part of the papyrus which deals with geometry by giving several numerical instances of the contents of barns. Unluckily, we do not know what was the usual shape of an Egyptian barn. But where it is defined by three linear measurements, say a, b, and c, the answer is always given as if he had formed the expression a times b times open bracket c plus half c closed bracket. He next proceeds to find the areas of certain rectilineal figures, in some of which he is certainly wrong, and then to find the area of a circular field of diameter 12, no unit of length being mentioned. In the latter case he gives the area as open bracket d minus 1/9 d quantity squared, where d is the diameter of the circle. This is equivalent to taking 3.1604 as the value of pi, the actual value being very approximately 3.1416. Lastly, Ahmes gives some problems on pyramids. These long proved incapable of interpretation, but Cantor and Eisenlohr have shown that Ahmes was attempting to find by means of data obtained from the measurement of some of the external dimensions of a building the ratio of certain other dimensions which could not be directly measured. His process is equivalent to determining the trigonometrical ratios of certain angles. The data and the results given agree closely with the dimensions of some of the existing pyramids. It is noticeable that all the specimens of Egyptian geometry which we possess deal only with particular numerical problems and not with general theorems, and even if a result be stated as universally true, it was probably proved to be so only by a wide induction. We shall see later that Greek geometry was from its commencement deductive. There are reasons for thinking that Egyptian geometry and arithmetic made little or no progress subsequent to the date of Ahmes's work. And though for nearly 200 years after the time of Thales, Egypt was recognized by the Greeks as an important school for mathematics, it would seem that, almost from the foundation of the Ionian school, the Greeks outstripped their former teachers. It may be added that Ahmes's book gives us much that idea of Egyptian mathematicians which we should have gathered from statements about it by the various Greek and Latin authors, some of whom lived nearly 15 centuries later. Previous to its translation it was commonly thought that these statements exaggerated the acquirements of the Egyptians, and its discovery must increase the weight to be attached to the testimony of these authorities. We know nothing of the applied mathematics, if there were any, of the Egyptians or Phoenicians. The astronomical attainments of the Egyptians and Chaldeans were no doubt considerable, though they were chiefly the results of observation. The Phoenicians are said to have confined themselves to studying what was required for navigation. Astronomy, however, lies outside of the range of this book. I do not like to conclude the chapter without a brief mention of the Chinese, since at one time it was asserted that they were familiar with the sciences of arithmetic, geometry, mechanics, optics, navigation, and astronomy nearly 3000 years ago, and a few writers were inclined to suspect, for no evidence was forthcoming, that some knowledge of this learning had filtered across Asia to the west. It is indeed almost certain that the Chinese were then acquainted with several geometrical or rather architectural implements, such as the rule, square, compass, and level, with a few mechanical machines such as the wheel and axle, that they knew of the characteristic property of the magnetic needle, and were aware that astronomical events occurred in cycles. But the careful investigations of L.A. Seydiot have shewn that the Chinese of that time had made no serious attempt to classify or extend the few rules of arithmetic or geometry which they knew, or to explain the causes of the phenomenon with which they were acquainted. The idea that the Chinese had made considerable progress in theoretical mathematics seems to have been due to a misapprehension of the Jesuit missionaries who went to China in the 16th century. In the first place, they failed to distinguish between the original science of the Chinese and the views which they found prevalent on their arrival, the latter being found on the work and teaching of Arab missionaries who had come to China in the course of the 13th century, and while there introduced the knowledge of spherical trigonometry. In the second place, finding that one of the most important government departments was known as the Board of Mathematics, they supposed that its function was to promote and superintend mathematical studies in the empire. Its duties were really confined to the annual preparation of an almanac, the dates and predictions in which regulated many affairs both in public and domestic life. All extant specimens of this almanac are extraordinarily inaccurate and defective. The only geometrical theorem with which, as far as I am aware, the ancient Chinese were acquainted was that in certain cases, namely when the ratio of the sides was 345 or 1 root 2, the area of the square described on the hypotenuse of a right angled triangle is equal to the sum of the areas of the squares described on the sides. It is barely possible that a few geometrical theorems which can be demonstrated in the quasi-experimental way of superposition were also known to them. Their arithmetic was decimal in notation, but their knowledge seems to have been confined to the art of calculation by means of the swan pen and the power of expressing the results in writing. Our acquaintance with the early attainments of the Chinese, slight though it is more complete than in the case of most of their contemporaries. It is thus specially instructive, and serves to illustrate the fact that a nation may possess considerable skill in the applied arts, while they are almost entirely ignorant of the sciences on which those arts are founded. From the foregoing summary it will be seen that our knowledge of the mathematical attainments of those who preceded the Greeks is very limited, but we may reasonably infer that from one source or another the early Greeks learned as much mathematics as is contained or implied in the Rhind papyrus, and it is probable that they were not acquainted with much more. In the next 6 chapters I shall trace the development of mathematics under Greek influence. End of chapter 1. Chapter 2. The Ionian and Pythagorean schools, 600 to 400 BC. First period, mathematics under Greek influence. This period begins with the teaching of Thales circa 600 BC and ends with the capture of Alexandria by the Mohammedans in or about 641 AD. The characteristic feature of this period is the development of geometry. It will be remembered that I commenced the last chapter by saying that the history of mathematics might be divided into 3 periods, namely that of mathematics under Greek influence, that of the mathematics of the Middle Ages and of the Renaissance, and lastly that of modern mathematics. The next four chapters, chapters 2, 3, 4, and 5, deal with the history of mathematics under Greek influence. To these it will be convenient to add one, chapter 6, on the Byzantine school, since through it the results of Greek mathematics were transmitted to Western Europe, and another, chapter 7, on the systems of numeration which were ultimately displaced by the system introduced by the Arabs. I should add that many of the dates mentioned in these chapters are not known with certainty and must be regarded as only approximately correct. Chapter 2. The Ionian and Pythagorean schools, circa 600 BC to 400 BC. With the foundation of the Ionian and Pythagorean schools we emerge from the region of antiquarian research and conjecture into the light of history. The materials at our disposal for estimating the knowledge of the philosophers of these schools previous to about the year 430 BC are however very scanty. Not only have all but fragments of the different mathematical treatises then written been lost, but we possess no copies of the elaborate histories of mathematics written about 325 BC by Eudemus, who was a pupil of Aristotle, and Theophrastus respectively. Luckily Proclus, who about 450 AD wrote a commentary on Euclid's Elements, was familiar with the history of Eudemus and gives a summary of that part of it which dealt with geometry. We have also a fragment of the general view of mathematics written by Geminus about 50 BC, in which the methods of proof used by the early Greek geometricians are compared with those current at a later date. In addition to these general statements we have biographies of a few of the leading mathematicians and some scattered notes in various writers which allusions are made to the lives and works of others. The original authorities are criticized and discussed at length in the works mentioned in the footnote to the heading of the chapter. The Ionian school. Thales. The founder of the earliest Greek school of mathematics and philosophy was Thales, one of the 7 sages of Greece, who was born about 640 BC at Miletus and died in the same town at about 550 BC. The materials for an account of his life consist of little more than a few anecdotes which have been handed down by tradition. During the early part of his life he was engaged partly in commerce and partly in public affairs, and to judge by 2 stories that have been preserved he was then as distinguished for shrewdness in business and readiness in resource as he was subsequently celebrated in science. It was probably as a merchant that Thales first went to Egypt, but during his leisure there he studied astronomy and geometry. He was middle-aged when he returned to Miletus. He then seems to have abandoned business and public life and to have devoted himself to the study of philosophy and science, subjects which in the Ionian, Pythagorean, and perhaps the Athenian schools were inextricably involved. He continued to live at Miletus till his death circa 550 BC. His views on philosophy do not here concern us. We cannot form any exact idea as to how Thales presented his geometrical teaching. We infer however from Proclus that it consisted of a number of isolated propositions which were not arranged in a logical sequence, but that the proofs were deductive, so that the theorems were not a mere statement of induction from a large number of special instances, as probably was the case with the Egyptian geometricians. The deductive character which he thus gave to the science is his chief claim to distinction. The following comprise all the propositions that we can now, with reasonable probability, refer back to him. 1. The angles at the base of an isosceles triangle are equal. Euclid 1:5. Proclus seems to imply that this was proved by taking another exactly equal isosceles triangle, turning it over, and then superposing it on the first, a sort of experimental demonstration. 2. If 2 straight lines cut one another, the vertically opposite angles are equal. Euclid 1:15. Thales may have regarded this as obvious, for Proclus adds that Euclid was the first to give a strict proof of it. 3. A triangle is determined if its base and base angles be given. Cf. Euclid 1:26. Apparently this was applied to find the distance of a ship at sea. the base being a tower, and the base angles being obtained by observation. Number 4. The sides of equiangular triangles are proportionals. Euclid 6.4, or perhaps rather Euclid 6.2. This is said to have been used by Thales when in Egypt to find the height of a pyramid. In a dialogue given by Plutarch, the speaker addressing Thales says, "Placing your stick at the end of the shadow of the pyramid, you make the sun's rays two triangles, and so proved that the height of the pyramid was the length of the stick as the shadow of the pyramid to the shadow of the stick." The king Amasis, who was present, is said to have been amazed by this application of abstract science, and the Egyptians seem to have been previously unacquainted with the theorem. Number 5. A circle is bisected by any diameter. This may have been enunciated by Thales, but it must have been recognized as obvious fact from the earliest times. Number 6. The angle in a semicircle is a right angle. Euclid 3.31. This appears to have been regarded as the most remarkable of the geometric achievements of Thales, and it is stated that on inscribing a right angled triangle in a circle he sacrificed an ox to the immortal gods. It is supposed that he proved the proposition by joining the center of the circle to the apex of the right angle, thus splitting the triangle into two isosceles triangles, and then applied the proposition above, proposition 1. If this be the correct account of his proof, he must have been aware that the sum of the angles of a right angled triangle is equal to the two right angles. It has been ingeniously suggested that the shape of the tiles used in paving floors may have afforded an experimental demonstration of the latter result, namely that the sum of the angles of a triangle is equal to the two right angles. We know from Eudemus that the first geometers proved the general property separately for three species of triangles, and it is not unlikely that they proved it thus. The area about a point can be filled by the angles of 6 equilateral triangles or tiles, hence the proposition is true for an equilateral triangle. Again, a rectangle, the sum of whose angles is 4 right angles, can be divided into 2 equal right angled triangles, hence the proposition is true for a right angled triangle, and it will be noticed that tiles of such a shape would give an ocular demonstration of this case. It would appear that this proof was given at first only in the case of isosceles right angled triangles, but probably it was extended later so as to cover any right angled triangle. Lastly, any triangle can be split into the sum of two right angled triangles by drawing a perpendicular from the biggest angle on the opposite side, and therefore again the proposition is true. The first of these proofs is evidently included into the last, but the early Greek geometers were timid about generalizing their proofs, and were afraid that any additional condition imposed on the triangle might vitiate the general result. Thales wrote on astronomy, and among his contemporaries was more famous as an astronomer than as a geometrician. It is said that one night when walking out he was looking so intently at the stars that he tumbled into a ditch, on which an old woman exclaimed, "How can you tell what's going on in the sky when you can't even see what's lying at your own feet?" An anecdote which was often quoted to illustrate the unpractical character of philosophers. Without going into astronomical details, it may be mentioned that he taught that a year contained 365 days, and not, as was previously reckoned, 12 months of 30 days each. According to some recent critics he believed the earth to be a disk, but it seems to be more probable that he was aware that it was spherical. He explained the causes of the eclipses both of the sun and the moon, and it is well known that he predicted a solar eclipse which would take place on or about the time he foretold. The actual date was May 28, 585 BC. But through this prophecy and its fulfilment gave extraordinary prestige to his teaching, and secured him the name of one of the 7 sages of Greece. It is most likely that he only made use of one of the Egyptian or Chaldean registers, which stated that solar eclipses recur on intervals of 18 years and 11 days. Among the pupils of Thales were Anaximander, Mamersus, and Mandriatus. Of the last two mentioned we know next to nothing. Anaximander is better known. He was born in 611 BC and died in 545 BC, and succeeded Thales as the head of the school at Miletus. According to Suidas, he wrote a treatise on geometry in which tradition says he paid particular attention to the properties of spheres, and dwelt at length on the philosophical ideas involved in the concept of infinity in space and time. He constructed terrestrial and celestial globes. He is alleged to have introduced the use of style or gnomon into Greece. This, in principle, consisted only of a stick stuck upright in a horizontal piece of ground. It was originally used as a sundial, in which case it was placed at the centre of three concentric circles, so that every 2 hours the end of its shadow passed from one circle to another. Such sundials have been found at Pompeii and Tusculum. It is said that he employed these styles to determine his meridian, presumably by marking the lines of shadow cast by the style at sunrise and sunset on the same day, and taking the plane bisecting the angle so formed. And thence, by observing the time of year when the noon altitude of the sun was greatest and least, he got the solstices. Thence, by taking half the sum of these noon altitudes of the sun at the 2 solstices, he found the inclination of the equator to the horizon, which determined the latitude of the place, and by taking half their difference he found the inclination of the ecliptic to the equator. There seems to be good reason to think that he did actually determine the latitude of Sparta, but it is more doubtful whether he really made the rest of these astronomical deductions. We need not here concern ourselves further with the successors of Thales. The school he established continued to flourish till about 400 BC, but as time went on its members occupied themselves more and more with philosophy and less with mathematics. We know very little of the mathematicians comprised in it, but they would have seemed to have devoted most of their attention to astronomy. They exercised but slight influence on the further advance of Greek mathematics, which was made almost entirely under the influence of the Pythagoreans, who not only immensely developed the science of geometry, but created a science of numbers. If Thales was the first to direct general attention to geometry, it was Pythagoras, says Proclus, quoting from Eudemus, who changed the study of geometry into the form of a liberal education, for he examined its principles to the bottom and investigated its theorems in an intellectual manner. And is accordingly to Pythagoras that we must now direct attention. End of part 1 of chapter 2. Chapter 2. The Ionian and Pythagorean schools 600 BC to 400 BC. Part 2. The Pythagorean school. Pythagoras. Pythagoras was born at Samos about 569 BC, perhaps of Tyrian parents, and died in 500 BC. He was thus a contemporary of Thales. The details of his life are somewhat doubtful, but the following account is, I think, substantially correct. He studied first under Pherecydes of Syros, and then under Anaximander. By the latter he was recommended to go to Thebes, and there or at Memphis he spent some years. After leaving Egypt he travelled in Asia Minor, and then settled at Samos, where he gave lectures but without much success. About 529 BC he migrated to Sicily with his mother, and with a single disciple who seems to have been the sole fruit of his labours at Samos. Thence he went to Tarentum, but very shortly moved to Croton, a Dorian colony in the south of Italy. Here the schools that he opened were crowded with an enthusiastic audience. Citizens of all ranks, especially those of the upper classes, attended, and even the women broke law which forbade their going to public meetings and flocked to hear him. Amongst his most attentive auditors was Theano, the young and beautiful daughter of his host Milo, who, in spite of the disparity of their ages, he married, and she wrote a biography of her husband, but unfortunately it is lost. Pythagoras was really a philosopher and moralist, but his philosophy and ethics, as we shall shortly see, rested on a mathematical basis. He divided those who attended his lectures into two classes: the listeners, or Pythagorii, and the mathematicians, or Pythagoriki. In general, a listener, after passing 3 years as such, could be initiated into the second class, to whom alone were confided the chief discoveries of the school. Following the modern usage, I confine the use of the word Pythagoreans to the latter class. The Pythagoreans formed a brotherhood with all things in common, holding the same philosophical beliefs, engaged in the same pursuits, and bound by oath not to reveal the teaching or secrets of the school. Their food was simple, their discipline severe, and their mode of life arranged to encourage self-command, temperance, purity, and obedience. They rose before the sun, and began by recalling the events of the preceding day. Next they made a plan for the day then commencing, and finally, on retiring to rest, they were expected to compare their performances with this plan. One of the symbols which they used for purposes of recognition was the pentagram, sometimes also called the triple triangle. To tripono trigono. The pentagram is merely a regular reentrant pentagon. It was considered symbolical of health, and the angles were denoted by letters of the word Eveia, see below page 39. The diphthong ea being replaced by a theta, it will be noticed that it consists of a single broken line, a feature to which certain mystical importance was attached. Iamblichus, to whom we owe the disclosure of this symbol, tells us how a certain Pythagorean, while travelling, fell ill at a roadside inn where he had put up for the night. He was poor and sick, but the landlord, who was a kind-hearted fellow, nursed him carefully, and spared no trouble or expense to relieve his pains. However, in spite of all efforts, the student got worse. Feeling that he was dying, and unable to make the landlord any pecuniary recompense, he asked for a board on which he inscribed the pentagram star. This he gave to his host, begging him to hang it up outside so that all passers-by might see it, and assuring them that he would not regret his kindness, as a symbol on it would ultimately shew. The scholar died and was honourably buried, and the board was duly exposed. After a considerable time had elapsed, a traveller one day riding by saw the sacred symbol. Dismounting, he entered the inn, and after hearing the story, handsomely remunerated the landlord. Such is the anecdote, which, if not true, is at least ben trovato. The majority of those who attended the lectures of Pythagoras were only listeners, but his philosophy was intended to colour the whole life, political and social, for all of his followers. In advocating self-control, government by the best men in the state, strict obedience to legally constituted authorities, and an appeal to eternal principles of right and wrong, he represented a view of society totally opposed to that of the democratic party of that time, and thus naturally most of the brotherhood were aristocrats. It had affiliated members in many of the neighbouring cities, and its method of organization and strict discipline gave it great political power, but like all secret societies it was an object of suspicion to those who did not belong to it. For a short time the Pythagoreans triumphed, but a popular revolt in 501 BC overturned the civil government, and in the riots that accompanied the insurrection the mob burnt the house of Milo, where the students lived, and killed many of the most prominent members of the school. Pythagoras himself escaped to Tarentum, and thence fled to Metapontum, where he was murdered in another popular outbreak in 500 BC. Though the Pythagoreans as a political society were thus rudely broken up and deprived of their head, they seem to have re-established themselves at once as a philosophical and mathematical society, having Tarentum as their headquarters. They continued to flourish for 100 or 150 years after the death of their founder, but they remained to the end a secret society and were therefore ignorant of the details of their history. Pythagoras himself did not allow the use of textbooks, and the assumption of his school was not only that all their knowledge was held in common and secret from the outside world, but that the glory of any fresh discovery must be referred back to their founder. Thus Hippasus, circa 470 BC, is said to have been drowned for violating his oath by publicly boasting that he had added the dodecahedron to the number of regular solids enumerated by Pythagoras. Gradually, as the society became more scattered, it was found convenient to alter this rule, and treatises containing the substance of their teaching and doctrines were written. The first book of the kind was composed by Philolaus, circa 410 BC, and we are told that Plato contrived to buy a copy of it. We may say that, during the early part of the 5th century before Christ, the Pythagoreans were considerably in advance of their contemporaries, but by the end of that time their more prominent discoveries and doctrines had become known to the outside world, and the centre of intellectual activity was transferred to Athens. Though it is impossible to separate precisely the discoveries of Pythagoras himself from those of his school of a later date, we know from Proclus that it was Pythagoras who gave geometry that rigorous character of deduction which it still bears, and made it the foundation of a liberal education. And there is a good reason to believe that he was the first to arrange the leading propositions of the subject in a logical order. It was also, according to Aristoxenus, the glory of his school that raised the arithmetic above the needs of the merchants. It was their boast that they sought knowledge and not wealth, or in the language of one of their maxims, a figure and a step forwards, not a figure to gain 3 oboli. Pythagoras was primarily a moral reformer and practical philosopher, but his system of morality and philosophy was built on a mathematical foundation. In geometry, he himself probably knew and taught the substance of what is contained in the first 2 books of Euclid, and was acquainted with a few other isolated theorems, including some elementary propositions on irrational magnitudes, while his successors added several of the propositions in the 6th and 11th books of Euclid. But it is thought that many of his proofs were not rigorous, and in particular that the converse of a theorem was frequently assumed without a proof. What philosophical doctrines were based on these geometrical results is now only a matter of conjecture. In the theory of numbers he was concerned with 4 different kinds of problems, which dealt respectively with polygonal numbers, ratio and proportion, the factors of numbers, and numbers in series, but many of his arithmetical inquiries, and in particular the questions on polygonal numbers and proportion, were treated by geometrical methods. Knowing that measurement was essential to the accurate definition of form, Pythagoras thought that it was also to some extent the cause of form, and he therefore taught that the foundation of the theory of the universe was to be found in the science of numbers. He was confirmed in this opinion by discovering that the note sounded by a vibrating string depended, other things being the same, only on the length of the string, and in particular that the lengths which gave a note its fifth and its octave were in the ratio 1 to 2/3 to 1/2. This may have been the reason why music occupied so prominent a position in the exercises of his school. He also believed that the distances of the heavenly bodies from the earth formed a musical progression, hence the phrase the harmony of the spheres. Taking the science of numbers as the foundation of his philosophy, he went on to attribute the properties to numbers and geometrical figures. For example, the cause of color was the number 5. The origin of fire was to be found in the pyramid. A solid body was analogous to the tetrad, which represented matter as composed of the 4 primary elements fire, air, earth, water, and so on. The tetrad, like the pentagram, was a sacred symbol, and the initiate's oath ran, and I provide here a translation from the Greek not provided by the book. I swear by him that gave to our soul the tetractys, which contains the fount and root of our eternal nature. The philosophical views of Pythagoras do not further concern us, and I now proceed to discuss his work on mathematics in rather greater detail. The Pythagoreans began dividing the subjects with which they dealt into 4 divisions: numbers, absolute or arithmetic, numbers applied or music, magnitudes at rest or geometry, and magnitudes in motion or astronomy. This quadrivium was long considered as constituting the necessary and sufficient course of study for a liberal education. Here I confine myself to describing the Pythagorean treatment of geometry and arithmetic. First, as to their geometry. We are of course unable to reproduce the whole body of Pythagorean teaching on this subject, but we gather from the notes of Proclus on Euclid, and from a few stray remarks in other writers, that it included the following propositions, most of which are on the geometry of areas. 1. It commenced with a number of definitions, which probably were rather statements connecting mathematical ideas with philosophy than explanations of the terms used. One has been preserved in the definition of a point as unity having position. 2. The sum of the angles of a triangle was shewn to be equal to 2 right angles, and in the proof which has been preserved, the results of the propositions Euclid 1.13 and the first part of Euclid 1.29 are quoted. The demonstration is substantially the same as that in Euclid, and it is most likely that the proofs there given of the 2 propositions last mentioned are also due to Pythagoras himself. 3. Pythagoras certainly proved the properties of right angled triangles which are given in Euclid 1.47 and 1.48. We know that the proofs of these propositions which are found in Euclid were of Euclid's own invention, and a good deal of curiosity has been excited to discover what was the demonstration which was originally offered by Pythagoras of the first of these theorems. It would seem most likely to have been one of the following. Alpha. Any square ABCD can be split up as in Euclid 2.4 into 2 squares BD and DK, and 2 equal rectangles AK and CK, that is equal to the square on FK, the square on EK, and 4 times the triangle AEF. But if the points taken G on BC, H on CD, and E on DA, so that BG, CH, and DE are each equal to AF, it can be easily shewn that EFGH is a square, and that the triangles AEF, BFG, CGH, and DHE are equal, and thus the square ABCD is also equal to the square on EF and 4 times the triangle AEF. Hence the square on EF is equal to the sum of the squares on FK and EK. Beta. Let ABC be a right angled triangle, A being the right angle. Draw AD perpendicular to BC. The triangles ABC and DBA are similar. Therefore, BC to AB is as AB to BD, and similarly BC to AC is equal to AC to DC. Hence, AB squared plus AC squared equals BC multiplied by the quantity BD plus DC. which equals bc squared. This proof requires a knowledge of the results of Euclid 2.2, 6.4, and 6.17, with all of which Pythagoras was acquainted. 4. Pythagoras is also credited with the discovery of theorems Euclid 144 and 145 with giving a solution of the problem of Euclid 2.14. It is said that on the discovery of the necessary construction for the problem last mentioned, he sacrificed an ox. But as his school had all things in common, the liberality was less striking than it seems at first. The Pythagoreans of a later date were aware of the extension given in Euclid 6.25, and Dr. Ullmann thinks that Pythagoras himself was acquainted with it, but this must be regarded as doubtful. It will be noticed that Euclid 2.14 is a geometrical solution of the equation x squared equals ab. 5. Pythagoras shewed that the plane about a point could be completely filled by equilateral triangles, by squares, or by regular hexagons, results that must have been familiar wherever tiles of these shapes were in common use. 6. The Pythagoreans were said to have solved the quadrature of the circle. They stated that the circle was the most beautiful of all plane figures. 7. They knew that there were 5 regular solids inscribable in a sphere, which was itself, they said, the most beautiful of all solids. 8. From their phraseology in the science of numbers and from other occasional remarks, it would seem that they were acquainted with the methods used in the 2nd and 5th books of Euclid, and knew something about irrational magnitudes. In particular, there is reason to believe that Pythagoras proved that the side and the diagonal of a square were incommensurable, and that it was this discovery which led the Greeks to banish the conceptions of number and measurement from their geometry. A proof of this proposition, which is not unlikely to be that due to Pythagoras, is given below. See page 61. Next, as to their theory of numbers. I have already remarked that in this the Pythagoreans were chiefly concerned with 1. Polygonal numbers, 2. The factors of numbers, 3. Numbers which form a proportion, and 4. Numbers in series. Pythagoras commenced his theory of arithmetic by dividing all numbers into even or odd, the odd numbers being termed gnomons. An odd number such as 2n plus 1 was regarded as the difference of 2 square numbers, that is, n plus 1 quantity squared, and n squared, and the sum of the gnomons from 1 to 2n plus 1 was stated to be a square number, vis-a-vis n plus 1 quantity squared, and its square root was termed a side. Products of 2 numbers were called a plane, and if a product had no exact root, it was termed an oblong. A product of 3 numbers was called a solid number, and if 3 numbers were equal, a cube. All of this has obvious reference to geometry, and the opinion was confirmed by Aristotle's remark that when a gnomon is put round a square, the figure remains a square, though it is increased in dimensions. Thus, in the annexed figure, which the gnomon AKC containing 11 small squares, when put round the square AC containing 5 squared small squares, makes a square HL containing 6 squared small squares. The number 2n squared plus 2n plus 1, the number 2n squared plus 2n, and the number 2n plus 1 possess special importance as representing the hypotenuse of 2 sides of a right-angled triangle. Cantor thinks that Pythagoras knew this fact before discovering the geometrical proposition Euclid 147. A more general expression for such numbers is m squared plus n squared, 2m times n, and m squared minus n squared. It will be noticed that the result obtained by Pythagoras can be deduced from these expressions by assuming m equals n plus 1. At a later time, Archytas and Plato gave rules which are equivalent to taking n equals 1. Diophantus knew the general rule. After this preliminary discussion, the Pythagoreans proceeded to the four special problems already alluded to. Pythagoras was himself acquainted with the triangular numbers, but probably not with any of the other polygonal numbers. The latter were discussed by later members of the school. A triangular number represents the sum of a number of counters laid in a row on a plane, the bottom row containing n and each succeeding row one less. It is therefore equal to the sum of the series n plus n minus 1 plus n minus 2 plus ... plus 2 plus 1. That is, to a half n multiplied by n plus 1. Thus the triangular number corresponding to 4 is 10. This is the explanation of the language of Pythagoras in the well-known passage in the Lucian where the merchant asks Pythagoras what he can teach him. Pythagoras replies, "I will teach you how to count." The merchant, "I know that already." Pythagoras, "How do you count?" Merchant, 1, 2, 3, 4. Pythagoras, "Stop! What you take to be 4 is 10, a perfect triangle, and our symbol." As to the work of the Pythagoreans on the factors of numbers we know very little. They classified numbers by comparing them with the sum of their integral factors, calling a number excessive, perfect, or defective, according as it was greater than, equal to, or less than the sum of these factors. These investigations led to no useful result. The third class of problems which they considered dealt with the numbers which formed a proportion. Presumably these were discussed with the aid of geometry and is done in the fifth book of Euclid. Lastly, the Pythagoreans were concerned with series of numbers in arithmetical, geometrical, harmonical, and musical progressions. The three progressions first mentioned are well known. 4 integers are said to be in musical progression when they are in the ratio a to 2ab over a plus b, half of a plus b to b. For example, 6, 8, 9, and 12 are in musical progression. After the death of Pythagoras, his teaching seems to have been carried on by Epicharmus and Hippasus, and subsequently by Philolaus, Archippus, and Lysis. About a century after the murder of Pythagoras, we find Archytas recognized as the head of the school. Archytas, circa 400 BC, was one of the most influential citizens of Tarentum and was made governor of the city no less than 7 times. His influence among his contemporaries was very great, and he used it with Dionysius on one occasion to save the life of Plato. He was noted for the attention he paid to the comfort and education of his slaves and of children in the city. He was drowned in a shipwreck near Tarentum, and his body washed on shore, a fit punishment in the eyes of the more rigid Pythagoreans for his having departed from the lines of study laid down by their founder. Several of the leaders of the Athenian school were among his pupils and friends, and it is believed that much of their work was due to his inspiration. The Pythagoreans at first made no attempt to apply their knowledge to mechanics, but Archytas is said to have treated it with the aid of geometry. He is alleged to have invented and worked out the theory of the pulley, and is credited with the construction of a flying bird and some other ingenious mechanical toys. He introduced various mechanical devices for constructing curves and solving problems. These were objected to by Plato, who thought that they destroyed the value of geometry as an intellectual exercise, and later Greek geometricians confined themselves to the use of 2 species of instruments, namely rulers and compasses. Archytas was also interested in astronomy. He taught that the earth was a sphere rotating round its axis in 24 hours, and round which the heavenly bodies moved. Archytas was one of the first to give a solution of the problem to duplicate a cube, that is, to find the side of a cube whose volume is double that of a given cube. This was one of the most famous problems of antiquity. See below page 38 to 42. The construction given by Archytas is equivalent to the following. On the diameter OA of the base of a right circular cylinder, describe a semicircle whose plane is perpendicular to the base of the cylinder. Let the plane containing the semicircle rotate around the generator through O, then the surface traced out by the semicircle will cut the cylinder in a tortuous curve. The curve will be cut by a right cone whose axis is OA and semi-vertical axis is, say, 60 degrees in a point P, such that the projection of OP on the base of the cylinder will be to the radius of the cylinder in the ratio of the side of the required cube to that of the given cube. The proof given by Archytas is of course geometrical. It will be enough here to remark that in the course of it he shews himself acquainted with the results of the propositions Euclid 3.18, 3.35, and 11.19. To shew analytically that the construction is correct, take OA as the axis of x, and the generator through O as axis of z, then with the usual notation in polar coordinates, and if a be the radius of the cylinder, we have for the equation of the surface described by the semicircle r equals 2a sine theta. For that of the cylinder, r sine theta equals 2a cos phi, and for that of the cone, sine theta times cos phi equals 1/2. These three surfaces cut in a point such that sine cubed theta equals 1/2, and therefore if ρ be the projection of OP on the base of the cylinder, then ρ cubed equals r sine theta quantity cubed equals 2a cubed. Hence the volume of the cube whose side is ρ is twice that of a cube whose side is a. I mention the problem and give the construction used by Archytas to illustrate how considerable was the knowledge of the Pythagorean school at that time. Theodorus. Another Pythagorean of about the same date as Archytas was Theodorus of Cyrene, who is said to have proved geometrically that the numbers presented by √3, √5, √6, √7, √8, √10, √11, √12, √13, √14, √15, and √17 are incommensurable with unity. Theaetetus was one of his pupils. Perhaps Timaeus of Locri and Brizo of Heraclea should be mentioned as other distinguished Pythagoreans of this time. Other Greek mathematical schools in 5th century BC. It would be a mistake to suppose that Miletus and Tarentum were the only places where in the 5th century Greeks were engaged in laying a scientific foundation for the study of mathematics. These towns represented the centers of chief activity, but there were few cities or colonies of any importance where lectures on philosophy and geometry were not given. Among these smaller schools I may mention those of Chios, Elea, and Thrace. The best known philosopher of the school of Chios was Euripides, who was born about 500 BC and died about 430 BC. He devoted himself chiefly to astronomy, but had studied geometry in Egypt and is credited with the solution of two problems, namely, one to draw a straight line from a given external point perpendicular to a given straight line, that's Euclid 1.12, and two, at a given point to construct an angle equal to a given angle, Euclid 1.23. Another important center was Elea in Italy. This was founded in Sicily by Xenophanes. He was followed by Parmenides, Zeno, and Melissus. The members of the Eleatic school were famous for the difficulties they raised in connection with the questions that required the use of infinite series, such for example as the well known paradox of Achilles and the tortoise, enunciated by Zeno, one of the most prominent members, who was born in 495 BC and was executed at Elea in 435 BC in consequence of some conspiracy against the state. He was a pupil of Parmenides, with whom he visited in Athens circa 455 to 450 BC. Zeno argued that if Achilles ran 10 times as fast as a tortoise, yet if the tortoise had, say, 1,000 yards start, it could never be overtaken. For when Achilles had gone the 1,000 yards, the tortoise would still be 100 yards in front of him. But by the time he had covered these 100 yards it would still be 10 yards in front of him, and so on forever. Thus Achilles would get nearer and nearer to the tortoise but never overtake it. The fallacy is usually explained by the argument that the time required to overtake the tortoise can be divided into an infinite number of parts, as stated in the question, but these get smaller and smaller in geometrical progression, and the sum of them all is a finite time. After the lapse of that time Achilles would be in front of the tortoise. Probably Zeno would have replied that this argument rests on the assumption that space is infinitely divisible, which is the question under discussion. He himself asserted that magnitudes were not infinitely divisible. These paradoxes made the Greeks look with suspicion on the use of infinite series and ultimately led to the invention of the method of exhaustions. The atomistic school, having its headquarters in Thrace, was another important centre. This was founded by Leucippus, who was a pupil of Zeno. He was succeeded by Democritus and Epicurus. Its most famous mathematician was Democritus, born in Abdera in 460 BC and is said to have died in 370 BC, who besides his philosophical works wrote on plane and solid geometry, incommensurable lines, perspective, and numbers. These works are all lost. But through several distinguished individual philosophers may be mentioned who during the 5th century lectured at different cities. They mostly seem to have drawn their inspiration from Tarentum, and towards the end of the century to have looked to Athens as the intellectual capital of the Greek world. And it is to the Athenian schools that we owe the next great advance in mathematics. End of chapter 2. Chapter 3. The schools of Athens and Cyzicus circa 420 BC to 300 BC. Part 1. It was towards the close of the 5th century before Christ that Athens first became the chief centre of mathematical studies. Several causes conspired to bring this about. During that century she had become, partly by commerce, partly by appropriating for her own purposes the contributions of her allies, the most wealthy city in Greece, and the genius of her statesmen had made her the centre on which the politics of the peninsula turned. Moreover, what states disputed her claim to political supremacy, her intellectual preeminence was admitted by all. There was no school of thought which had not at some time that century been represented at Athens by one or more of its leading thinkers, and the ideas of the new science, which was being so eagerly studied in Asia Minor and Graecia Magna, had been brought before the Athenians on various occasions. Anaxagoras. Among the most important of the philosophers who resided at Athens and prepared the way for the Athenian school I may mention Anaxagoras of Clazomenae, who was almost the last philosopher of the Ionian school. He was born in 500 BC and died in 428 BC. He seems to have settled in Athens about 440 BC and there taught the results of the Ionian philosophy. Like all members of that school, he was much interested in astronomy. He asserted that the sun was larger than the Peloponnesus. This opinion, together with some attempts he had made to explain various physical phenomena which had been previously supposed to be due to the direct action of the gods, led to a prosecution for impiety, and he was convicted. While in prison he is said to have written a treatise on the quadrature of the circle. The Sophists can hardly be considered as belonging to the Athenian school any more than Anaxagoras can, but like him they immediately preceded and prepared the way for it, so that it is desirable to devote a few words to them. One condition for success in public life at Athens was the power of speaking well, and as the wealth and power of the city increased, a considerable number of Sophists settled there, who undertook amongst other things to teach the part of oratory. Many of them also directed the general education of their pupils, of which geometry usually formed a part. We are told that two of those who are usually termed Sophists made a special study of geometry. These were Hippias of Elis and Antipho, and one made a special study of astronomy, and that was Meton, after whom the Metonic cycle is named. The first of these geometricians, Hippias of Elis (circa 420 B.C.), is described as an expert arithmetician, but he is best known to us through his invention of a curve called the quadratrix, by means of which an angle could be trisected or indeed divided in any given ratio. If the radius of a circle rotate uniformly around the center O from a position OA through a right angle OB, and in the same time a straight line drawn perpendicular to OB move uniformly parallel to itself from the position OA to BC, the locus of their intersection will be the quadratrix. Let OR and MQ be the positions of these lines at any time. Let them cut in P a point on the curve. Then the ratio angle AOP to angle AOB will equal the ratio OM to OB. Similarly, if OR prime be another position of the radius, then the ratio of angle AOP prime to angle AOB will equal the ratio OM prime to OB. Therefore, angle AOP to angle AOP prime will equal the ratio OM to OM prime. Therefore, angle AOP prime to angle P prime OP will equal the ratio OM prime to M prime M. Hence, if the angle AOP be given and it be required to divide any given ratio, it is sufficient to divide OM in that ratio at M prime and draw the line M prime P prime, and then OP prime will divide AOP in the required ratio. If OA be taken as the initial line OP equals R, the angle AOP equals theta and OA equals A, then we have the ratio theta to half pi will be equal to the ratio r sine pi to A. And the equation of the curve is pi r equals 2a theta times cosecant theta. Hippias devised an instrument to construct the curve mechanically, but constructions which involved the use of any mathematical instruments except a ruler and a pair of compasses were objected to by Plato and rejected by most geometricians of a subsequent date. Antipho. The second sophist whom I mentioned was Antipho, circa 420 B.C. He is one of very few writers among the ancients who attempted to find the area of a circle by considering it as the limit of an inscribed regular polygon with an infinite number of sides. He began by inscribing an equilateral triangle. On each side in the smaller segment he inscribed an isosceles triangle, and so on ad infinitum. Bryso. Another mathematician, probably about the same time, who attacked the quadrature problem in a similar way to that used by Antipho, was Bryso of Heraclea, who seems to have been a Pythagorean. See above, page 31. It is said that he began by inscribing and circumscribing squares, and finally obtained polygons between whose areas the area of the circle lay. It is possible but not probable that for some time he taught at Athens. No doubt there were other cities in Greece where similar and equally meritorious work was being done, though the record of it has now been lost. I have mentioned the investigations of these writers, partly in order to give the idea of the kind of work of which was then going on all over Greece, but chiefly because they were the immediate predecessors of those who created the Athenian school. The history of the Athenian school begins with the teaching of Hippocrates about 420 BC. The school was established on a permanent basis by the labours of Plato and Eudoxus, and together with the neighbouring school of Cyzicus continued to extend on the lines laid down by these three geometricians until the foundation, about 300 BC, of the new university at Alexandria drew most of the talent of Greece thither. Eudoxus was among the most distinguished of the Athenian mathematicians, and it is also reckoned as the founder of the school of Cyzicus. The connection between this school and that of Athens was very close, and it is now impossible to disentangle their histories. It is said that Hippocrates, Plato, and Theaetetus belonged to the Athenian school, while Eudoxus, Menaechmus, and Aristippus belonged to that of Cyzicus. There was always a constant intercourse between the two schools. The earliest members of both had been under the influence either of Archytas or of his pupil Theodorus of Cyrene, and there was no difference in their treatment of the subject, so that they may be conveniently treated together. Before discussing the work of the geometricians of these schools in detail, I may note that they were especially interested in three problems, namely 1. The duplication of a cube, that is, the determination of the side of a cube whose volume is double that of a given cube, and 2. The trisection of an angle, and 3. The squaring of a circle, that is, the determination of a square whose area is equal to that of a given circle. Now the first two of these problems, considered analytically, require the solution of a cubic equation, and since a construction by means of circles whose equations are of the form x squared plus y squared plus ax plus by plus c equals 0, and straight lines whose equations are of the form alpha x plus beta y plus gamma equals 0, cannot be equivalent to the solution of a cubic equation. The problems are insoluble if our constructions we restrict ourselves to the use of circles and straight lines, i.e. Euclidean geometry. If the use of conic sections be permitted, both of these questions can be solved in many ways. The third problem is equivalent to finding a rectangle whose sides are equal respectively to the radius and to the semiperimeter of the circle. These lines have been long known to be incommensurable, but it is only recently that it has been shewn by Lindemann that the ratio cannot be the root of a rational algebraic equation. Hence this problem is also insoluble by Euclidean geometry. The Athenians and Cyzicians were thus destined to fail in all three problems, but the attempts to solve them led to the discovery of many new theorems and processes. Besides attacking these problems, the later Platonic school collected all the geometrical theorems then known and arranged them systematically. These collections comprise the bulk of the propositions in Euclid's Elements, books 1 to 9, 11, and 12, together with some of the more elementary theorems in conic sections. Hippocrates. Hippocrates of Chios, who must be carefully distinguished from his contemporary Hippocrates of Kos, the celebrated physician, was one of the greatest of the Greek geometricians. He was born about 470 BC at Chios, and began life as a merchant. The accounts differ as to whether he was swindled by the Athenian custom house officials who were stationed at the Chersonese, or whether one of his vessels was captured by an Athenian pirate near Byzantium. But at any rate, somewhere about 430 BC he came to Athens to try to recover his property in the law courts. A foreigner was not likely to succeed in such a case, and the Athenians seem only to have laughed at him for his simplicity, first in allowing himself to be cheated, and then in hoping to recover his money. While prosecuting his cause, he attended the lectures of various philosophers, and finally, in all probability to earn a livelihood, opened a school of geometry himself. He seems to have been well acquainted with the Pythagorean philosophy, though there is no sufficient authority for the statement that he was ever initiated as a Pythagorean. He wrote the first elementary textbook of geometry, a textbook on which Euclid's Elements was probably founded, and therefore he may be said to have sketched out the lines on which geometry is still taught in English schools. It is supposed that the use of letters and diagrams to describe a figure was made by him or introduced about his time, as he employs expressions such as the point on which the letter A stands, and the line on which AB is marked. Cantor, however, thinks that the Pythagoreans had previously been accustomed to represent the 5 vertices of the pentagram star by the letters upsilon, gamma, iota, theta, alpha. See above, page 21. And though this was a single instance, they may perhaps have used the method generally. The Indian geometers have never employed letters to aid them in the description of their figures. Hippocrates also denoted the square on a line with the word venoms, and thus gave the technical meaning to the word power, which it still retains in algebra. There is reason to think that this use of the word was derived from the Pythagoreans, who are said to have enunciated the result of the proposition as Euclid 147 in the form that the total power of the sides of a right-angled triangle is the same as that of the hypotenuse. In this textbook, Hippocrates introduced the method of reducing one theorem to another, which being proved, the thing proposed necessarily follows, of which plan the reductio ad absurdum is a particular case. No doubt the principle had been used occasionally before, but he drew attention to it as a legitimate mode of proof which was capable of numerous applications. He may be said to have introduced the geometry of the circle. He discovered that similar segments of a circle contain equal angles, that the angle subtended by the chord of a circle is greater than, equal to, or less than a right angle, as a segment of the circle containing it is less than, equal to, or greater than a semicircle. Euclid 331, and probably several other of the propositions in the third book of Euclid. It is most likely that he also enunciated the propositions that similar circles are to one another as the squares of their diameters, and that similar segments are as the square of the chords. The proof given in Euclid of the first of these theorems is believed to be due to Hippocrates, but the latter mathematician does not seem to have realized that all circles were similar. The most celebrated discoveries of Hippocrates were, however, in connection with the quadrature of the circle and the duplication of the cube, and it was owing to his influence that these problems played such a prominent part in the history of the Athenian school. The following propositions will sufficiently illustrate the method by which he attacked the quadrature problem. Alpha. He commenced by finding the area of a lune contained between the semicircle of a quadrantal arc standing on the same chord. This he did as follows. Let ABC be an isosceles right-angled triangle inscribed in the semicircle ABOC, whose center is O. On AB and AC as diameters describes semicircles as in the figure. Then, since BC squared equals AC squared plus AB squared, Euclid 147, therefore by Euclid 12.2, the area of a half circle on BC equals the sum of the areas of the half circles on AC and AB. Take away the common parts, therefore area of triangle ABC equals the sum of the areas of loones AECD and AFBG. Hence the area of the loon AECD is equal to half of that of the triangle ABC. He next inscribed half a regular hexagon ABCD in a semicircle whose center was O, and on OA, AB, BC, and CD as diameters described semicircles, of which those on OA and AB are drawn in the figure. Then AD is double any of the lines OA, AB, BC, and CD. Therefore AD squared equals OA squared plus AB squared plus BC squared plus CD squared. Therefore area of half circle ABCD equals the sum of the areas of the half circles on OA, AB, BC, and CD. Take away the common parts, therefore the area of the trapezium ABCD equals 3 multiplied by the loon AEBF plus half circle on OA. If therefore the area of this latter loon be known, so is that of the semicircle described on OA as diameter. According to Simplicius, Hippocrates assumed that the area of this loon was the same as the area of the loon found in proposition alpha. If this be so, he was of course mistaken, as in the case he is dealing with, a loon contained between a semicircle and a sextantal arc standing on the same chord, but it seems probable that Simplicius misunderstood Hippocrates. Hippocrates also enunciated various other theorems which connected with loons, which have been collected by Bretschneider and Ellmann, of which theorem last given is a typical example. I believe they are the earliest instances in which areas bounded by curves were determined by geometry. The other problem to which Hippocrates turned his attention was the duplication of the cube, that is, the determination of the side of a cube whose volume is double that of a given cube. This problem was known in ancient times as the Delian problem, a consequence of a legend that the Delians had consulted Plato on the subject. In one form of the story, which is related by Philoponus, it is asserted that the Athenians in 430 BC, when suffering from the plague of eruptive typhoid fever, consulted the oracle at Delos as to how they could stop it. Apollo replied, they must double the size of his altar, which was in the form of a cube. To the unlearned suppliants nothing seemed more easy, and a new altar was constructed, either having each of its edges doubled that of the old one, for which it followed the volume was increased eightfold, or by placing a similar cubic altar next to the old one. Whereupon, according to the legend, the indignant god made the pestilence worse than before, and informed a fresh deputation that it was useless to trifle with him, as his new altar must be a cube and have a volume exactly double that of his old one. Suspecting a mystery, the Athenians applied to Plato, who referred them to the geometricians, and especially to Euclid, who had made a special study of the problem. The introduction of the names of Plato and Euclid is an obvious anachronism. Eratosthenes gives a somewhat similar account of its origin, but with King Minos as the propounder of the problem. Hippocrates reduced the problem of duplicating the cube to that of finding two means between one straight line alpha and another twice as long 2 alpha. If these means be x and y, we have a is to x as x is to y as y is to 2 alpha, from which it follows that x cubed equals 2a cubed. It is in this form that the problem is always presented now. Formerly, any process of solution by finding these means was called a mesolabum. Hippocrates did not succeed in finding a construction for these means. End of chapter 3, part 1. Chapter 3. The schools of Athens and Cyzicus, circa 420 BC to 300 BC. Part 2. Plato. The next philosopher of the Athenian school who requires mention here was Plato, who was born in Athens in 429 BC. He was, as is well known, a pupil for 8 years of Socrates, and much of the teaching of the latter is inferred from Plato's dialogues. After the execution of his master in 399 BC, Plato left Athens, and being possessed of a considerable wealth, he spent some years travelling. It was during this time that he studied mathematics. He visited Egypt with Eudoxus, and Strabo says that in his time the apartments they occupied at Heliopolis were still shewn. Thence Plato went to Cyrene, where he studied under Theodorus. Next he moved to Italy, where he became intimate with Archytas, the then head of the Pythagorean school, Eurytas of Metapontum, and Timaeus of Locri. He returned to Athens about the year 380 BC and formed a school of students in a suburban gymnasium called the Academy. He died in 348 BC. Plato, like Pythagoras, was primarily a philosopher, and perhaps his philosophy should be regarded as founded on the Pythagorean rather than on the Socratic teaching. At any rate, it, like that of the Pythagoreans, was coloured with the idea that the secret of the universe was to be found in number and in form. Hence, as Eudemus says, he exhibited on every occasion the remarkable connection between mathematics and philosophy. All the authorities agree that, unlike many later philosophers, he made a study of geometry or some exact science an indispensable preliminary to that of philosophy. The inscription over the entrance to his school ran, "Let none ignorant of geometry enter my door," and on one occasion an applicant who knew no geometry is said to have been refused admission as a student. Plato's position as one of the masters of the Athenian mathematical school rests not so much on his individual discoveries and writings as on the extraordinary influence he exerted on his contemporaries and successors. Thus the objection that he expressed to the use of the construction of curves of any instruments other than rulers and compasses was at once accepted as canon which must be observed in such problems. It is probably due to Plato that subsequent geometricians began the subject with a carefully compiled series of definitions, postulates, and axioms. He also systematized the methods which could be used in attacking mathematical questions, and in particular directed attention to the value of analysis. The analytical method of proof begins by assuming that the theorem or problem is solved, and thence deducing some result. If the result be false, the theorem is not true, or the problem is incapable of solution. If the result be known to be true, and if the steps be reversible, we get by reversing them a synthetic proof. But if the steps are not reversible, no conclusion can be drawn. Numerous illustrations of the method will be found in any modern textbook on geometry. If the classification of the methods of legitimate induction given by Mill in his work on logic had been universally accepted, and every new discovery in science had been justified by a reference to the rules laid down, he would, I imagine, have occupied a position in reference to modern science somewhat analogous to that which Plato occupied in regard to the mathematicians of his time. Almost the only extant instance of a mathematical theorem attributed to Plato is the following, which is traditionally assigned to him. If CAB and DAB be two right-angled triangles having one side AB in common, their other sides AD and BC parallel and their hypotenuses AC and BD at right angles, then if these hypotenuses cut in P, we have the ratio PC to PB is to PB to PA is to PA to PD. This theorem was used in duplicating the cube, for if such triangles can be constructed having PD equals 2 times PC, the problem will be solved. it is easy to make an instrument by which the figures can be drawn. Eudoxus. Of Eudoxus, the third great mathematician of the Athenian school and the founder of that at Cyzicus, we know very little. He was born in Cnidus in 408 BC. Like Plato, he went to Tarentum and studied under Archytas, the then head of the Pythagoreans. Subsequently, he travelled with Plato to Egypt and then settled at Cyzicus, where he founded the school of that name. Finally, he and his pupils moved to Athens. There he seems to have taken some part in public affairs, and to have practiced medicine, but the hostility of Plato and his own unpopularity as a foreigner made his position uncomfortable, and he returned to Cyzicus or Cnidus shortly before his death. He died while on a journey to Egypt in 355 BC. His mathematical work seems to have been of a high order of excellence. He discovered most of what we know as the fifth book of Euclid, and proved it in much the same form as that of which it is there given. He discovered some theorems on what was called the golden section. The problem to cut a line AB in the golden section, that is, to divide it, say, at h, in extreme and mean ratio, that is, so that AB to AH equals the ratio AH to HB, is solved in Euclid 2:11, and was probably known to the Pythagoreans at an early date. If we denote AB by L, AH by A, and HB by B, the theorems that Eudoxus proved are equivalent to the following algebraical identities. Number 1. Quantity A plus 1/2 L all squared equals 5 multiplied by quantity 1/2 times L all squared. That's Euclid 13:1. Number 2. Conversely, if 1 be true, and AH be taken equal to A, then AB will be divided at H in the golden section. That's Euclid 13:2. Number 3. Quantity B plus 1/2 A all squared equals 5 multiplied by quantity 1/2 times A all squared. Euclid 13:3. Number 4. L squared plus B squared equals 3 multiplied by A squared. That's Euclid 13:4. Number 5. L plus A is to L as L is to A, which gives another golden section, and that's Euclid 13:5. These propositions were subsequently put by Euclid at the commencement of his 13th book, but they might have been equally well placed toward the end of the second book. All of them are obvious algebraically, since L equals A plus B and A squared equals B times L. Eudoxus further established the method of exhaustions, which depends on the proposition that if from the greater of two unequal magnitudes there be taken more than its half, and from the remainder more than its half, and so on, there will at length remain a magnitude less than the least of the proposed magnitudes. This proposition was placed by Euclid as the first proposition of the 10th book of his Elements, but in most modern school editions it is printed at the beginning of the 12th book. By the aid of this theorem, the ancient geometers were able to avoid the use of infinitesimals. The method is rigorous, but awkward of application. A good illustration of its use is to be found in the demonstration of Euclid 12:2, namely that of the square of the radius of one circle is to the square of the radius of another circle, as the area of the first circle is to the area of which is neither less nor greater than the area of the second circle, and which therefore must be exactly equal to it. The proof given by Euclid, as was usual, is completed by a reductio ad absurdum. Eudoxus applied the principle to shew that the volume of a pyramid or cone is 1/3 that of the prism or cylinder of the same base and the same altitude. That's Euclid 12:7 and 10. Some writers attribute the proposition Euclid 12:2 to him, but not Hippocrates. Eudoxus also considered certain curves other than the circle, but there seems to be no authority for the statement, which is found in some old books, that he studied the properties of the conic sections. He discussed some of the plane sections of the anchor ring, that is, of the solid generated by the revolution of a circle around a straight line lying on its plane. But he assumed that the line did not cut the circle. A section by a plane through this line consists of two circles. If the plane be moved parallel to itself, the sections are lemniscates. When the plane first touches the surface, the section is a figure of 8, generally called Bernoulli's lemniscate, whose equation is r squared equals a squared multiplied by cosine 2 theta. All this is explained at length in books on solid geometry. Eudoxus applied these curves to explain the apparent progressive and retrograde motions of the planets, but we do not know the method he used. Eudoxus constructed an orrery and wrote a treatise on practical astronomy, in which he adopted a hypothesis previously propounded by Philolaus 409 BC to 356 BC, and supposed a number of moving spheres to which the sun, moon, and stars were attached, and by which their rotation produced the effects observed. In all he required 27 spheres. As observations became more accurate, subsequent astronomers who accepted his theory had continually to introduce fresh spheres to make the theory agree with the facts. The work of Aratus on astronomy, which was written about 300 BC, is still extant, is founded on that of Eudoxus. Plato and Eudoxus were contemporaries. Among Plato's pupils were the mathematicians Leodamus, Nicolaides, Amyclas, and to their school belonged Leon, Theodius, both of whom wrote textbooks on plane geometry, Cyzicenus, Thasus, Hierotimus, Philippus, and Theaetetus. Among the pupils of Eudoxus are reckoned Menaechmus and his brother Dinostratus, who applied the quadratics to the duplication and trisection problems, and Aristoteus. Menaechmus. Of the above mentioned mathematicians, Menaechmus requires special attention. He was born about 375 BC and died about 325 BC. He was a pupil of Eudoxus and probably succeeded him as head of the school at Cyzicus. Menaechmus acquired a great reputation as a teacher of geometry and was for that reason appointed one of the tutors to Alexander the Great. In answer to Alexander's request to make his proofs shorter, he made the well-known reply, "In the country, sire, there are private and even royal roads, but in geometry there is only one road for all." Menaechmus was the first to discuss the conic sections, which were long called the Menaechmian triads. He divided them into 3 classes and investigated their properties, not by taking different plane sections of a fixed cone, but by keeping his plane fixed and cutting it by different cones. He shewed that the section of the right cone by a plane perpendicular to the generator is an ellipse, and if the cone be acute angled, a parabola, and if it be right angled, a hyperbola. If it be obtuse angled, he gave the mechanical construction for curves of each class. It seems almost certain he was acquainted with the fundamental properties of these curves, but some writers think that he failed to connect them with the sections of the cone for which he had discovered, and there is no doubt that he regarded the latter not as plane loci, but as curves drawn on the surface of a cone. He also shewed how these curves could be used in either of the following ways to give a solution of the problem to duplicate a cube. In the first of these he pointed out that 2 parabolas having a common vertex, axes at right angles, and such that the latus rectum of the one is double that of the other, will intersect in another point whose abscissa or ordinate will give a solution. For using analysis, if the equations of the parabolas be y squared equals 2ax and x squared equals ay, they intersect in a point whose abscissa is given by x cubed equals 2a cubed. It is probable that this method was suggested by the form in which Hippocrates had cast the problem, namely, to find x and y so that a is to x equals x is to y equals y to 2a, when we have x squared equals ay and y squared equals 2ax. The second solution given by Menaechmus was as follows. Describe a parabola of latus rectum L. Next, describe a rectangular hyperbola, the length of whose real axis is 4L, and having for its asymptotes the tangent at the vertex of the parabola and the axis of the parabola. Then the ordinate and abscissa of the point of intersection of the curves are the mean proportionals between L and 2L. This is at once obvious by analysis. The curves are x squared equals L times y and x times y equals 2 times L squared. These cut in a point determined by x cubed equals 2 times L cubed and y cubed equals 4 times L cubed. Hence, L is to x equals x is to y equals y is to 2L. Of the other members of these schools, the only mathematicians of first-rate power were Aristeas and Theaetetus, whose works are entirely lost. We know, however, that Aristeas wrote on the 5 regular solids and on conic sections, and that Theaetetus developed the theory of incommensurable magnitudes. The only theorem we can now definitely ascribe to the latter is that given by Euclid in the 9th proposition of the 10th book of the Elements, namely, that the squares on two commensurable right lines have one to the other a ratio which a square number has to a square number, and conversely. But the squares on two incommensurable right lines have one to the other a ratio which cannot be expressed as that of a square number to a square number, and conversely. This theorem includes the results given by Theodorus. See above, page 31. The contemporaries or successors of these mathematicians wrote some fresh textbooks on the elements of geometry and the conic sections, introduced problems concerned with finding loci, and efficiently carried out the work commenced by Plato of systematizing the knowledge already acquired. Aristotle. An account of the Athenian school would be incomplete if there were no mention of Aristotle, who was born in Stagira in Macedonia in 384 BC and died at Chalkis in Euboea in 322 BC. Aristotle, however, deeply interested though he was in natural philosophy, was chiefly concerned with mathematics and mathematical physics as supplying illustrations of correct reasoning. A small book containing a few questions on mechanics, which is sometimes attributed to him, is of doubtful authority, but though in all probability it is due to another writer, it is interesting partly as shewing that the principles of mechanics were beginning to excite attention, and partly as containing the earliest known employment of letters to indicate magnitudes. The most instructive parts of the book are the dynamical proof of the parallelogram of forces for the direction of the resultant, and the statement that, if alpha be a force, beta be the mass to which it is applied, gamma the distance through which it is moved, and delta the time of the motion, then alpha will move 1/2 beta through 2 gamma in time delta, or through gamma in time 1/2 delta. But the author goes on to say that it does not follow that 1/2 alpha will move beta through 1/2 gamma in time delta, because 1/2 alpha may not be able to move beta at all. For 100 men may drag a ship 100 yards, but it does not follow that one man can drag it 1 yard. The first part of this statement is correct and is equivalent to the statement that an impulse is proportional to the momentum produced, but the second part is wrong. The author also states the fact that what is gained in power is lost in speed, and therefore that two weights which keep a weightless lever in equilibrium are inversely proportional to the arms of the lever. This, he says, is the explanation why it is easier to extract teeth with a pair of pincers than that with the fingers. Among the other questions raised but not answered are why a projectile should ever stop, and why carriages with large wheels are easier to move than with small. I ought to add that the book contains some gross blunders, and as a whole is not able or suggestive as might be inferred from the above extracts. End of chapter 3. Chapter 4, Part 1 of a short account of the history of mathematics. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This is a reading by Paul King, pjk.scripts.mit.edu/pkj. A short account of the history of mathematics by Rouse. Chapter 4. The First Alexandrian School, circa 300 BC to 30 BC. Part 1. The earliest attempt to found a university, as we understand the word, was made at Alexandria. Richly endowed, supplied with lecture rooms, libraries, museums, laboratories, gardens, and all the plant and machinery that ingenuity could suggest, it became at once the intellectual metropolis of the Greek race, and remained so for 1,000 years. It was particularly fortunate in producing within the first century of its existence three of the greatest mathematicians of antiquity, Euclid, Archimedes, and Apollonius. They laid down the lines on which mathematics were subsequently studied, and largely owing to their influence the history of mathematics centres more or less round that of Alexandria until the destruction of the city by the Arabs in 641 AD. The city and university of Alexandria were created under the following circumstances. Alexander the Great had ascended the throne of Macedonia in 336 BC at the early age of 20, and by 332 BC he had conquered or subdued Greece, Asia Minor, and Egypt. Following the plan he had adopted whenever a commanding site had been left unoccupied, he founded a new city on the Mediterranean near one mouth of the Nile, and he himself sketched out the ground plan and arranged for drafts of Greeks, Egyptians, and Jews to be sent to occupy it. The city was intended to be the most magnificent in the world, and the better to secure this, its erection was left in the hands of Dinocrates, the architect of the temple of Diana at Ephesus. After Alexander's death in 323 BC, his empire was divided, and Egypt fell to the lot of Ptolemy, who chose Alexandria as the capital of his kingdom. A short period of confusion followed, but as soon as Ptolemy was settled on the throne, say 306 BC, he determined to attract as far as he was able learned men of all sorts to his new city, and he at once began the erection of the university buildings on a piece of ground immediately adjoining his palace. The university was ready to be opened somewhere around 300 BC, and Ptolemy, who wished to secure for its staff the most eminent philosophers of the time, naturally turned to Athens to find them. The great library, which was a central feature of the scheme, was placed under Demetrius Phalereus, a distinguished Athenian, and so rapidly did it grow that within the first 40 years it, together with the Egyptian annex, possessed about 600,000 rolls. The mathematical department was placed under Euclid, who was thus the first, as he was one of the most famous of the mathematicians of the Alexandrian school. It happens that contemporaneously with the foundation of this school, the information on which our history is based becomes more ample and certain. Many of the works of the Alexandrian mathematicians are still extant, and we have besides an invaluable treatise by Pappus, described below, in which their best known treatises are collated, discussed, and criticized. It curiously turns out that just as we begin to be able to speak with certainty on the subject matter which was taught, we find that our information as to the personality of the teachers becomes uncertain, and we know very little of the lives of the mathematicians mentioned in this and the next chapter, even the dates at which they lived being frequently uncertain. The 3rd century before Christ. Euclid. This century produced 3 of the greatest mathematicians of antiquity, namely Euclid, Archimedes, and Apollonius. The earliest of these was Euclid. Of his life we know next to nothing, save that he was of Greek descent, and he was born about 330 BC. He died about 275 BC. It would appear that he was well acquainted with the Platonic geometry, but he does not seem to have read Aristotle's works, and these facts are supposed to have strengthened the tradition that he was educated at Athens. Whatever may have been his previous training and career, he proved most successful a teacher when settled at Alexandria. He impressed his own individuality on the teachings of the new university to such an extent that to his successors and almost to his contemporaries the name Euclid meant, as it does to us, the book or the books he wrote, and not the man himself. Some of the medieval writers went so far as to deny his existence, and with the ingenuity of philologists they explained that the term was only a corruption of the Greek words for key and geometry. The former word was presumably derived from kleis. I can only explain the meaning assigned to dies by the conjecture that as the Pythagoreans said that the number 2 symbolized a line, possibly a schoolman may have thought that it could be taken as indicative of geometry. From the meagre notices of Euclid which have come down to us, we find that the saying that there is no royal road to geometry was attributed to Euclid as well as to Menaechmus, but it is an epigrammatic remark which has had many imitators. Euclid is also said to have insisted that knowledge was worth acquiring for its own sake, and Stobaeus, who is somewhat doubtful an authority, tells us that when a lad who had just begun geometry asked, "What do I gain by learning all this stuff?" Euclid made his slave give the boy some coppers, since, said he must make a profit out of what he learns. According to Pappus, Euclid, in making the use of the work of his predecessors when writing the Elements, dealt most gently with those who had in any way advanced the science, and the Arabian writers, who may perhaps convey to us the traditions of Alexandria, uniformly represent him as a gentle and kindly old man. Euclid was the author of several works, but his reputation had rested mainly on his Elements. This treatise contains a systematic exposition of the leading propositions of elementary geometry, exclusive of conic sections, and of the theory of numbers. It was at once adopted by the Greeks as the standard textbook for the elements of pure mathematics, and it is probable that it was written for that purpose and not as a philosophical attempt to shew that the results of geometry and arithmetic are necessary truths. The modern text is founded on an edition prepared by Theon, the father of Hypatia, and is practically a transcript of Theon's lectures at Alexandria circa 380 AD. There is at the Vatican a copy of an older text, and we have besides quotations from the work and references to it by numerous writers of various dates. From these sources we gather that the definitions, axioms, and postulates were rearranged and slightly altered by subsequent editors, but that the propositions themselves are substantially as Euclid wrote them. As to the matter of the work, the geometrical part is to a large extent a compilation from the works of previous writers. Thus the substance of books 1 and 2 is probably due to Pythagoras, that of book 3 to Hippocrates, that of book 5 to Eudoxus, and the bulk of books 4, 6, 11, and 12 to the later Pythagorean or Athenian schools. But this material was rearranged, obvious deductions were omitted, for example the proposition that the perpendiculars from the angular points of a triangle on the opposite sides meet in a point was cut out, and in some cases new proofs substituted. The part concerned with the theory of numbers would seem to have been taken from the works of Eudoxus and Pythagoras, except that portion, book 10, which deals with irrational magnitudes. This later may be founded on the lost book of Theaetetus, but much of it is probably original, for Proclus says that while Euclid arranged the propositions of Eudoxus, he completed many of those of Theaetetus. The way in which the propositions are proved, consisting of enunciation, statement, construction, proof, and conclusion, is due to Euclid. So also is the synthetical character of the work, each proof being written out as a logically correct train of reasoning, but without any clue to the method by which it was obtained. The defects of Euclid's Elements as a textbook of geometry have been often stated. The most prominent are these. 1. The definitions and axioms contain many assumptions which are not obvious, and in particular the so-called axiom about parallel lines is not self-evident. 2. No explanation is given as to the reason why the proofs take the form in which they are presented, that is, the synthetical proof is given but not the analysis by which it was obtained. 3. There is no attempt made to generalize the results arrived at. For instance, the idea of an angle is never extended so as to cover the case where it is equal to or greater than two right angles. The second half of the 33rd proposition in the 6th book, as it is now printed, appears to be an exception, but it is due to Theon and not due to Euclid. 4. The principle of superposition as a method of proof might be used more frequently with advantage. 5. The classification is imperfect. And 6. The work is unnecessarily long and verbose. On the other hand, the propositions in Euclid are arranged so as to form a chain of geometrical reasoning, proceeding from certain almost obvious assumptions by easy steps to results of considerable complexity. The demonstrations are rigorous, often elegant, and not too difficult for a beginner. Lastly, nearly all the elementary metrical as opposed to graphical properties of space are investigated. The fact that for 2000 years it has been the recognized textbook of the subject raises further a strong presumption that it is not unsuitable for the purpose. During the last few years some determined efforts have been made to displace it in our schools, but the majority of teachers still appear to regard it as the best foundation for geometrical teaching that has yet been published. The book has been, however, generally abandoned on the continent, though apparently with doubtful advantage to the teaching of geometry. To these arguments in its favour may be added the fact that some of the greatest mathematicians of modern times, such as Descartes, Pascal, Newton, and Lagrange, have advocated its retention as a textbook. And Lagrange said that he who did not study geometry in Euclid would be as one who should learn Latin or Greek from modern works written in those tongues. It must also be remembered that there is an immense advantage in having a single textbook in universal use in a subject like geometry. The unsatisfactory condition of the teaching of geometrical conics in schools is a standard illustration of the evils likely to arise from using different textbooks in such a subject. Some of the objections urged against Euclid do not apply to certain of the recent school editions of his Elements. I do not think that all the objections above stated can fairly be urged against Euclid himself. He published a collection of problems generally known as the Dedomena or Data. This contains 95 illustrations of the kind of deductions which frequently have to be made in analysis, such as that if one of the data of the problems under consideration be that one angle of some triangle in the figure is constant, then it is legitimate to conclude that the ratio of the area of the rectangle under the sides containing the angle to the area of the triangle is known. It's proposition 66. Pappus says that the work was written for those who wish to acquire the power of solving problems. It is in fact a graduated series of exercises in analysis, and this seems a sufficient answer to the second objection. Euclid also wrote a work called Peri Division, or De Divisionibus, which is known to us only through an Arabic translation, which may be itself imperfect. This is a collection of 36 problems on the division of areas into parts which bear to one another a given ratio. It is not unlikely that this was only one of several such collections of examples, possibly including the fallacies and the porisms, but even by itself it shews that the value of exercises and riders was fully recognized by Euclid. I may here add a suggestion thrown out by De Morgan, who is perhaps the most acute of all the modern critics of Euclid. He thinks it likely that the Elements were written towards the close of Euclid's life, and that their present form represents the first draft of the proposed work, which, with the exception of the 10th book, Euclid did not live to revise. If this opinion is correct, then it is probable that Euclid would in his revision have removed the fifth objection. The geometrical parts of the Elements are so well known that I do no more than to allude to them. The first 4 books and book 6 deal with plane geometry. The theory of proportion of any magnitudes is discussed in book 5, and books 11 and 12 treat of solid geometry. On the hypothesis that the Elements are the first draft of Euclid's proposed work, it is possible that book 13 is a sort of appendix containing some additional propositions which would have been put ultimately in one of the other earlier books. Thus, as mentioned above, see page 46, that the first 5 propositions which deal with a line cut in golden section might be added to the second book. The next 7 propositions are concerned with the relations between certain incommensurable lines in plane figures, such as the radius of a circle and the sides of an inscribed regular triangle, pentagon, hexagon, and decagon, which are treated by the methods of the 10th book and as an illustration of them. The 5 regular solids are discussed in the last 6 propositions. Bretschneider is inclined to think that the 13th book is a summary of part of the lost work of Aristeas, but the illustrations of the methods of the 10th book are due most probably to Theaetetus. Books 7, 8, 9, and 10 of the Elements are given up to the theory of numbers. The mere art of calculation or loistiki was taught to boys when quite young. It was stigmatized by Plato as childish and never received much attention from Greek mathematicians, nor was it regarded as forming part of a course of mathematics. We do not know how it was taught, but the abacus certainly played a prominent part in it. The scientific treatment of numbers was called arithmetic, which I have here generally translated as the science of numbers. It had special reference to ratio, proportion, and the theory of numbers. It is with this alone that most of the extant Greek works deal. In discussing Euclid's arrangement of the subject, we must therefore bear in mind that those who attended his lectures were already familiar with the art of calculation. The system of numeration adopted by the Greeks is described later, see below, chapter 7. But it was so clumsy that it rendered the scientific treatment of numbers much more difficult than of geometry. Hence Euclid commenced his mathematical course with plane geometry. At the same time it must be observed that the results of the second book, though geometrical in form, are capable of expression in algebraical language, and the fact that numbers could be represented by lines was probably insisted on at an early stage and illustrated by concrete examples. This graphical method of using lines to represent numbers possesses the obvious advantage of leading to proofs which are true for all numbers rational or irrational. It will be noticed that among other propositions in the second book we get geometrical proofs of the distributive and commutative laws, of rules for multiplication, and finally geometrical solutions to the equations a multiplied by quantity a minus x equals x squared, that is, x squared plus ax minus a squared equals 0. That's Euclid 2:11. And x squared minus ab equals 0. Euclid 2:14. The solution of the first of these equations is given of the form the square root of quantity a squared plus 1/2 a squared end of square root minus half a. The solutions of the equations ax squared minus bx plus c equals 0 and ax squared plus bx minus c equals 0 are given later in Euclid 6:28 and 6:29, the cases when a equals 1 can be deduced from the identities proved in Euclid 2:5 and 6, but it is doubtful if Euclid would have detected this. The results of the fifth book, in which the theory of proportion is considered, apply to any magnitudes, and therefore are true of numbers as well as of geometrical magnitudes. In the opinion of many writers, this is the easiest way of treating the theory of proportion on a scientific basis, and was used by Euclid as the foundation on which he built the theory of numbers. The theory of proportion given in this book is believed to be due to Eudoxus. The treatment of the same subject in the seventh book is less elegant and is supposed to be a reproduction of the Pythagorean teaching. This double discussion of proportion is, as far as it goes, in favour of the conjecture that Euclid did not live to revise the work. In books 7, 8, and 9 Euclid discusses the theory of rational numbers. He commences the seventh book with some definitions founded on the Pythagorean notation. In propositions 1 to 3 he shews that if, in the usual process for finding the greatest common measure of two numbers, that the least divisor be unity, the numbers must be prime, and he thence deduces the rule for finding their GCM. Propositions 4 to 22 include the theory of fractions, which he bases on the theory of proportion. Among other results he shews that AB equals BA, proposition 16. In propositions 23 to 34 he treats of prime numbers, given many of the theorems in modern textbooks on algebra. In propositions 35 to 41 he discusses the least common multiple of numbers and some miscellaneous problems. The eighth book is chiefly devoted to numbers in continued proportion, i.e. in a geometrical progression, and the cases where one or more is a product square or cube are specially considered. In the ninth book Euclid continues the discussion of geometrical progressions, and in proposition 35 he enunciates the rule for the summation of a series of n terms, though the proof is given only for the case where n is equal to 4. He also develops the theory of primes, shews that the number of primes is infinite, proposition 20, and discusses the properties of odd and even numbers. He concludes by shewing how to construct a perfect number, proposition 36. In the 10th book Euclid treats of irrational magnitudes, and since Greeks possessed no symbolism for surds he was forced to adopt a geometrical representation. Propositions 1 to 21 deal generally with incommensurable magnitudes. The rest of the book, namely propositions 22 to 117, is devoted to the discussion of every possible variety of lines which can be represented, such as the square root of a plus or minus the square root of b, where a and b denote commensurable lines. There are 25 species of such lines, and that Euclid could detect and classify them all is in the opinion of so competent an authority as Nesselmann as the most striking illustration of his genius. It seems at first almost impossible that this could have been done without the aid of algebra, but it is tolerably certain that it was actually effected by abstract reasoning. No further advance in the theory of incommensurable magnitudes was made until the subject was taken up by Leonardo and Cardan after an interval of more than 1000 years. In the last proposition of the 10th book, 10.117, the side and diagonal of a square are proved to be incommensurable, and the proof is so short and easy that I may quote it. If possible, let the side be to the diagonal in a commensurable ratio, namely that of two integers a, b. Suppose this ratio is reduced to its lowest term, so that a and b have no common divisor other than unity, that is, they are prime to one another. Then, by Euclid 147, b squared equals 2a squared, and therefore b squared is an even number. Therefore b is an even number. Hence, since a is prime to b, a must be an odd number. Again, since it has been shewn that b is an even number and b may be represented by 2n, therefore 2n quantity squared equals 2 times a squared. Therefore a squared equals 2 times n squared. Therefore a squared is an even number. Therefore a is an even number. Thus the same number a must be both odd and even, which is absurd. Therefore the side and diagonal are incommensurable. Henkel believes that this proof was due to Pythagoras, and was inserted on account of its historical interest. This proposition is also proved in another way by Euclid 10.9. In addition to the Elements and the last two collections of writers above mentioned, which are extant, Euclid wrote the following books on geometry. 1. An elementary treatise on conic sections in 4 books. 2. A book on curved surfaces, probably chiefly cone and cylinder. 3. A collection of geometrical fallacies, which were to be used as exercises in the detection of errors. And 4. A treatise on the porisms arranged in the 3 books. All of these are lost, but the work on porisms was discussed at such length by Pappus that some writers have thought it possible to restore it. In particular, Chasles in 1860 published what purports to be a reproduction of it, in which will be found the conceptions of cross ratios and projections, in fact those ideas of modern geometry which Chasles and other writers of this century have used so largely. This is brilliant and ingenious, and of course no one can prove that it is not exactly what Euclid wrote, but the statements of Pappus concerning this book have come to us only in mutilated form, and De Morgan frankly says that he found them unintelligible, an opinion in which most of those who read them will, I think, concur. Euclid published 2 books on optics, namely the Optics and the Catoptrica. Of these the former is extant. A work which purports to be the latter exists in the form of an Arabic translation, but there is some doubt as to whether it represents the original work written by Euclid. In any case the text is extraordinarily corrupt. The Optics commences with the assumption that the objects are seen by rays emitted from the eye in straight lines. For if light proceeded from the object we should not, as we often do, fail to perceive a needle on the floor. It contains 61 propositions founded on 12 assumptions. The Catoptrica consists of 31 propositions dealing with reflections in planes, convex and concave mirrors. The geometry of both books is ingenious. Euclid also wrote the Phenomena, a treatise on geometrical astronomy. It contains references to the work of Autolycus and to some book on spherical geometry by an unknown writer. Pappus asserts that Euclid also composed a book on the elements of music. This may refer to Sectio Canonis, which is by Euclid and deals with musical intervals. To these works I may add the following little problem, which occurs in the Palatine Anthology and is attributed by tradition to Euclid. Quote, a mule and a donkey were going to market laden with wheat. The mule said, if you give me one measure, I should carry twice as much as you, but if I give you one, we should bear equal burdens. Tell me, learned geometrician, what were their burdens? Now, it is impossible to say whether the question is genuine, but it is the kind of question he might have asked. It will be noticed that Euclid dealt only with magnitudes and did not concern himself with their numerical measures, but it would seem from the works of Aristarchus and Archimedes that this was not the case with all the Greek mathematicians of that time. As one of the works of the former is extant, it will serve as another illustration of Greek mathematics of this period. Aristarchus. Aristarchus of Samos, born in 310 BC and died in 250 BC, was an astronomer rather than a mathematician. He asserted at any rate, as a working hypothesis, that the sun was the centre of the universe, and that the earth revolved around the sun. This view, in spite of the simple explanation it afforded of various phenomena, was generally rejected by his contemporaries, but his propositions on the measurement of the sizes and distances of the sun and moon were accurate in principle, and his results were generally accepted, for example by Archimedes in Samitis, see below page 73, as approximately correct. There are 19 theorems, of which I select the seventh as a typical illustration, because it shews the way in which the Greeks evaded the difficulty of finding the numerical value of surds. Aristarchus observed the angular distance between the moon when dichotomized and the sun, and found it to be 29/30 of a right angle. It is actually about 89 degrees 21 minutes, but of course his instruments were of the roughest description. He then proceeded to shew that the distance of the sun is greater than 18 and less than 20 times the distance of the moon in the following manner. Let S be the sun, E be the earth, and M the moon. Then, when the moon is dichotomized, that is, when the bright part which we see is exactly a half circle, the angle between MS and ME is a right angle. With E as the center and the radii ES, EG bisecting the angle, AEF as in the figure, let EM produced cut AF in H. The angle AEM is by hypothesis 1/30 of a right angle. Hence we have angle AEG to angle AEH has the ratio 1/4 right angle to 1/30 of a right angle, or the ratio 15:2. AG to AH, that is the tangent of AEG to the tangent of AEH, is also 15:2. Again, the ratio FG squared to AG squared is equal to the ratio EF squared to EA squared, Euclid 6:3, which is a ratio of 2:1, Euclid 147. Therefore, FG squared to AG squared is greater than the ratio 49:25. Therefore, FG to AG is a ratio greater than the ratio 7:5. Therefore, AF to AG, that ratio is greater than the ratio 12:5, and therefore the ratio AE to AG greater than the ratio 12:5. Now, compounding the statements in alpha was the AG to AH ratio, which would be equal to the tangent AEG to AEH being greater than 15:2, and statement beta being the statement AE to AG being greater than the ratio of 12:5. So compounding those ratios, we have the ratio AE to AH being greater than 18:1. But the triangles EMS and EAH are similar. Therefore, ES to EM is a ratio greater than 18:1. I will leave the second half of the proposition to amuse any reader who may care to prove it. The analysis is straightforward. In somewhat similar way Aristarchus found the ratio of the radii of the Sun, Earth, and Moon. End of chapter 4, part 1.